Assalamualaikum warahmatullahi wabarakatuh. So this is the second video for chapter 3. So in this video I will cover on the process safety. Okay, now let's have a look. What is the behind of process safety? Okay, so basically for the process safety analysis, there is a act that we need to fulfill or we need to comply. So this process safety basically required by law under Occupational Safety and Health Act 1994. Okay, so employees during the analysis, employees must be involved in the hazard analysis, and this analysis must be updated every 5 years. So the other thing is the employee also need to be trained in safe work practice. So associate with the identified hazards. This safety analysis basically can be updated based on the needs, the current condition. For example, like current condition, we have a pandemic, right? So this safety analysis also can be updated. Okay, analysis of product and process safety. So this analysis basically is performed by Safety, Health and Environmental Department. So we need to analyze the SHE impact of technology. So it is important to carry out every stage of a project using the project technical information. Okay, so we start with the research concept. So under research concept, we have information like MSDS info, chemistry info, and we also have the HSE department will do analysis based on MSDS reviewed and also major hazard review. So next, moving on to the second stage, which is conceptual design. So conceptual design, we have a PFD, equipment list, vessel design, reactor models. So basically all of these information are available. So based on the available information, we can perform analysis such as FMEA, HAZAN, PP analysis. So these three analysis basically cover different scope. So later on I will explain in detail. So next is preliminary design. So in preliminary design, we have PNID. So in PNID, we have a process control methodology, detail, H and WB, offsite layout. Okay, based on this information, we can perform the hazard analysis, emergency procedures, and also effluent summary. Okay, next stage is detailed design. So in the detailed design, we have mechanical designs. The info that we can obtain is instrument specifications. Under this detailed design, we can perform the analysis, which is quantitative, risk analysis, and also fault tree analysis. So lastly, the operation stage. So in the operation stage, we have a plot plans. So we have information of isometrics based on the build spec. So from this information, we can perform as build, hazard, and also operator training. Okay, failure mode effect analysis is FMEA. So FMEA is an early stage approach to identifying problem with a technology. The scope of FMEA is safety, environment, operation, and also feasibility. So this FMEA, we can use a different version for process design and also product design. The goal of this FMEA is to identify the critical technical risk using a semi-quantitative procedure. Okay, the other type of analysis is HAZOP. So HAZOP is a hazard and operability study. So this hazard analysis is detailed and structured assessment of process design. So basically we will cover only on the process design such as our equipment. So the review of P&ID sections notes by specified group. Okay, basically PID section is reviewed by the process engineer, instrument engineer, SHE expert, mechanical engineer, operation expert, and also other expert as needed. So basically this hazard analysis we will not perform in silo. We will perform in a team of consists of many areas like process, instrument, SHE, mechanical, and operations. Okay, so basically the procedure for the HAZOP, we start with study note. I think this one you already learned inside the safety subject. So I just recall back. So we start with study note. So from the study note, we need to know the design intention. So from the design intention, we need to evaluate the worst case, the deviation that can be occurred to the specified equipment. So the example of deviation is like no or not. So for example, we have reactor. Okay, if the reactor, the temperature is less, how could it be? If the temperature of the reactor is small, how could it be? So first thing first, we need to list down the possible deviation that can be occur from the equipment itself. So from the deviation, we need to we need to think what can happen, what is the causes of that deviations. If temperature of the reactor is too high, it can cause overheating. So some sort like that. You need to do the deviations based on what you can expect from the equipment. Okay. So, okay, after we list down the causes, consequence, safeguard, risk ranking, and recommendation, and then we need to evaluate back. Is there any other deviations? If yes, if yes, need to go back to the deviations at the third stage back. If no, we proceed to the other notes. Notes is a like in a reactor, for example. Study note 1, we focus on the temperature. Study note 2, we focus on the pressure. Study note 2, we focus on the flow. So if we already come up with the safeguard, risk ranking, and recommendation for the first note, and we found that there is no other deviation, and then we can proceed with the second notes. Inside your assessment, you need to perform this HAZOP analysis to your equipment. Okay, so quantitative hazard analysis. So basically FMEA and also HAZOP is belong to quantitative hazard analysis. So the function of these two analyses help you to brainstorm possible failure mode, help modify the design, the feasibility design, the early stage design to prevent this mode from occurring. And from this analysis also, we can know are relatively cheap to carry out. And the last point is do not provide quantification of the risk. Okay, so for the quantitative method, for example, like reliability analysis, fault tree analysis, we can estimate probability of an event based on known probabilities such as the probability of failure of an instrument. So basically, the analysis that we perform, we need to in advance think the possible worst scenario can happen. So we will dealing with the probability in this quantitative analysis. So under this quantitative method also require detailed design as well as substantial effort, which may include the test program for equipment that is not already rated. Okay, this is the fault tree analysis. So basically, for fault tree analysis, it's quite similar with the concept that we learn inside the process control. If you still remember, we learned about the Boolean algebra inside the process control. So the method to do the fault tree analysis, we use this Boolean algebra. So we will determine overall probability of the hazard. Okay, under this fault tree analysis also, we can modify design until desired hazard rate is achieved. How to modify the design? We can introduce the duplicates, increase the test of maintenance rate. Okay, the other thing is we can specify higher performance equipment. Okay, just want to recall back, this is the AND gate, this is the OR gate. So AND gate, the relationship is Z here is equal to A dot B dot C. So dot mean multiply A multiply B multiply C. So in order to make sure this Z happen, all these three must happen simultaneously. Okay, for OR gate, Z here is equal to A plus B plus C. So if one of event such as event A occur, this Z will trigger. Okay. So this is the fault tree analysis for vessel. Okay, we can see here, this is the OR gate. All this is OR gate. So basically this fault tree analysis is not complete. Supposedly we need to have the other block diagram here. Okay, we can we just see one example here. Okay, in case of dirt inside the vessel, okay, dirt or other. So if dirt happen, and of course this vessel, the PRV will block. Remember, if OR gate, if one incident happen, then the output will be triggered like PRV block. So in here also OR gate, if one of these happen, the PRV will fail to give a adequate discharge at pressure danger level. Okay, and lastly for the AND gate, if the vessel explodes, it need these two incidents to happen, which is PRV fail and also flow in is greater than flow out. So please remember, AND gate, you need all the incidents to happen in order to occur Z is equal to A plus B. Z is equal to A dot B. That means these two must be occur in order this one to be occurred. If OR gate, if one of these occurred, and it shows that this PRV will be failed. Okay, so standard for safety instrumentation. We have a ISA as 84.01, which is Safety Instrumented System, SIS. Okay, this ISA is a US standard for emergency shutdown system. The goal for the standard is to protect people, not plant or profit. So this ISA is equivalent to IEC 61511. So the other standard for safety instrumentation is IEC 61508 and also 61511. So IEC is the International Electrotechnical Commissions. So this is the international standard for safety instrumented system. The standards define requirement for sensor solvers. Solvers is a logic like OR gate, AND gate, and finite element, which is valve switches. So basically inside this standard, it's explain in detail the standard for operating the sensor, logic, and also valve according to conditions. Okay, safety integrity levels. So ISA define 3 levels of safety integrity depending on the availability of the SIS. So availability here meaning time the system is available over total time. Over total time of the systems. So from this formula we can evaluate the safety integrity levels. So for level 1, the availability is around 90 to 99%. So it indicates that system redundancy for this seal 1 is non-redundant. For seal 2, the availability is around 99 to 99.9%. So under this level, the system is partially redundant. Under seal 3, the availability is 99.9 to 99.99%. So for seal 3, the system is totally redundant. So what is meant by the redundant? Redundant systems mean instrumentation is duplicate. The failure of the system may be caused by a failure of instrument components. So it's integrate. That means the instrument is integrate, and the failure of one system is a failure caused by instrument components, the integration of components. So the required seal we should determine during a process hazard analysis. So it depends on risk of operator, exposure, and also injury. The actual system seal can be calculated knowing the type of instrument, their reliability, the test rate, and the intrinsic hazard rate. So basically this one can be calculated using fault trees. Remember back the fault tree analysis, we have the OR gate, AND gate, and we have the value 1 or 0. So from there we can calculate the seal. Okay, the seal determines the type of instrumentation that should be used and the degree of redundancy. So redundant instrumentation. Higher level of redundancy of thread system give higher seal. Okay, normally if the seal is high, that means if the system fail, it's caused by the high level of redundancy of the components. So if we have one instrument, if it signals, so the plant will goes down. So the probability of the incident is caused by the probability of incident is equal to the probability of instrument failure, and the probability of a spurious trip is equal to false positive rate of one instrument only. So if we have two instruments, one out of two voting, that means one out of two instruments. So one instrument signal, the plant will goes down. So the probability of incident reduced by duplications. So the probability of spurious trip double. Okay, if two out of two voting, the probability of incident worse than single instrument. Twice likelihood that system is down. Okay, just now we only have one instrument, and we can directly know if there is a signal, the plant goes down is caused by that one instrument. But under this condition, we have two instrument. If two instrument give a signal, and the system will goes down, the likelihood will become twice. Okay, the probability of spurious trip will reduce under this 2 out of 2 voting. So if we have 3 instruments, 2 out of 3 voting, this is the best overall trade-off between reducing incident rate and spurious trip rate. So one malfunctioning instrument does not cause trip or prevent detection of real incident. So if there is one instrument malfunctions, it will not cause the plant to goes down. So it will, if there is two instrument out of three malfunctioning, then it will give a signal. Okay, human error. The intervention of well-trained operator is a vital layer in process safety. Human error is always a possibility. So this one, the human error normally can come from the unsafe practice during operation, the housekeeping itself, no proper housekeeping. So the housekeeping normally is performed by the human, so that one can cause the human error also. This is the pyramid of danger. So we start with the lowest one, which is unsafe behavior and unsafe environment. Okay, and then we moving on the unaccomplished incidents and recordable injuries, serious injuries, and death. So for your informations, in a company, we always calculate the lost time injury. So if that company can maintain their lost time injury at good ranking, that means that company, there is no accident occur inside that company, and that company operate their plant in a safe manner. If their LTI, lost time injury, if there is a death inside that company, the lost time injury ranking will goes down. And normally every company have their own ranking of LTI. So we the safety community normally will evaluate the ranking of this LTI. So from the LTI, we can know that there is a death or there is a serious injury inside that occur inside the company. Okay, I think that's all for this subchapter 3.2. So I will explain on the assessments later on with you all during our class. Thank you.